Fine. Robert, please.
Okay, thank you very much. Yeah, welcome back, everyone. I think it was a very dense and difficult day so far. So I will not take too much of your time or kind of bombard you too much longer with talking. I just want to explain a little bit what I had in mind and what this is about. And as Maria said, it's a voluntary thing. It's a for fun thing. I think it is really useful to get a little kind of background impression on how the methods I've been talking about so far, in particular, the Srg and the no-core shell model works. And I think the best way to experience that is with a little do-it-yourself exercise. So really at the computational level, to experience and see with your own little program and with your own eyes what these methods are doing, how they are working, and what you can expect from them. The basic idea, and in order to illustrate that, I'm just showing a screen share of my web browser. The basic idea is kind of illustrated in this little computational project. So this is a website that I just kicked up for the school, and I sent the link around via Slack. So in the Ab Initio channel on Slack, you can find the link to this page. You can also read it up here. It's lengthy, therefore I didn't even bother to specify it in the lecture earlier. So if you don't have it from Slack, it's written here. It's Theorie, IKP, Physik, TU Darmstadt DE, and then TNP, that's our working group, Theoretical Nuclear Physics, and then index.php, !.ggi for Galilei Institute. But just use the link in Slack if you want to go there. You will find the slides of my lectures already complete up to the third lecture from today, and there's even a little more in there, which I will come back to in the last lecture. But the important thing for now is this extra section here on the computational project. There's a little bit of a description what I have in mind, and there is a link to a zip file, which essentially contains 4 files. 2 of them are real matrix elements from a harmonic oscillator Jacobi basis for a chiral 2+3 nucleon Hamiltonian. And these are kind of the starting point for our experiments with Srg and the NCSM. So that's something you cannot easily generate yourself. So therefore, this is provided. There are 2 files, one for the kinetic energy and one for the interaction part of the Hamiltonian. And this is kind of what we need, and I'll show you in detail how they look like and what to do with them in a minute. In addition, in this zip file, there is a Mathematica notebook and a PDF file, which shows all the content of this Mathematica notebook. I'm kind of an old-fashioned Mathematica fan, but I do not assume that anybody here is either using or has Mathematica available. So the idea is really, I just use Mathematica to illustrate what I have in mind, but then you are essentially free to go and use the preferred environment that you also use in your daily PhD work, for example. And for many of you, that might be Python, which is absolutely fine. So from the computational aspects, what you really need from your programming environment is super basic. So it's not a big problem. You don't need computing time. And Python is perfectly adequate for doing that. I'm just so used to Mathematica that it's quicker for me to do it there. And therefore, I'll show you the rough outline of this project in Mathematica. And as I said, the notebook and a PDF version of this notebook is contained in this zip file. So you can use that as kind of guidance or a starting point for your own experiments. Okay. So please, if there are questions at any point, interrupt me or use the chat. I mean, we can talk, that's great. So if you just unmute and ask questions, that would be great. That's more lively then. So I will switch from this website, which you can get via this link on Slack, to this Mathematica notebook I mentioned to illustrate a little bit further how this project is set up and what it implies. Okay, so you should see now a Mathematica front end. So what I had in mind is that based on these three-body matrix elements that you will find in the file, you can really start to experiment yourselves. There's two obvious tasks or topics that you can work on. Number one is the Srg evolution in three-body space, which is already pretty fancy and pretty advanced. This is something that people were not able to do something like 8 years ago. So that's not a toy problem, actually. And then as a second step, or if you don't want to do the Srg stuff, you can start right away with that, a calculation in an NCSM spirit. So that means solving the matrix eigenvalue problem of this Hamiltonian in basis representation. For those of you who are really interested in algorithms and programming, I think there's a really nice opportunity to explore this magic Langshaw's algorithm that I mentioned in the lecture, and essentially I spelled it out in the lecture. And this is something that you can also try yourself based on these matrix elements. And this is a very fun and illustrative example. So this is also an optional thing you can do. For all of that, you need a few inputs, and these are mainly the matrix elements. So let's have a look at what I did here and what I provided in this little zip file. I'll go through this Mathematica steps where I have essentially the most stupid implementation of an Srg evolution and no-Cauchy model calculation. I'm absolutely sure that you can do better than this, and I would encourage you to do better than this, but this is kind of a starting point which shows what to expect and what kind of necessary and critical steps are involved in the numerical treatment. Okay, so now I have a little initialization part up here. This is really only to set a few constants, so it's useful to have the nucleon mass, which is this Mn in convenient units, and to have h bar c in convenient units. Obviously, this is something which enters in the kinetic energy. So this is good to have. And I just defined these constants. All my units here will be MEVs for energies and Fermis for the length scale. And then I just set a few options for plotting commands in Mathematica. So you will not need that if you do Python, or you will need other things. So this is just to make plots look nicer. The first thing, or the starting point for all of that, is having the initial Hamiltonian, as I call it. So this is kind of the output of all the modeling of chiral effective field theory for the 2 and 3 nucleon forces. And it is the output of a computation of the harmonic oscillator matrix elements for this chiral Hamiltonian. So everything we are doing here is built on a basis or matrix representation, which uses a three-body harmonic oscillator basis. And I didn't put in the calculation of this matrix, these matrix elements itself, because this is really tedious stuff. And it is not really instructive to look into details there. So therefore, these matrix elements are provided in 2 data files. And I'll just read in these files. I have put them onto my desktop. You can do the same, and I just tell Mathematica to look at the desktop directory for those files. And I can just show you what's in these files. There's one file that's called Kinetic. That's for the kinetic energy. Emax 20, so this E is this principal harmonic oscillator quantum number in three-body space. And it just tells you that this is a basis size of up to 20 in this oscillator quantum number. So that means it also allows you to do up to Nmax 20 NCSM calculations. And it has h bar omega, so this HW is for h bar omega 20. That means we use a basis frequency of 20 MeV for this calculations. And if I look into that file, that's a plain ASCII table. So it's just matrix elements for the kinetic energy. And it's not really the full kinetic energy. It's just a non-trivial structure. Therefore, you have this pretty simple numbers like 30 in there. And it's just rows and columns which build the matrix representation of the kinetic energy in this Jacobi harmonic oscillator basis. Yeah? And there's a similar file for the interaction. The second file is called Chi2b 3b, so for chiral two-body, three-body. So that's a combination of the two and the three-body force in three-body space. And in Mathematica slang, I use these import commands to simply read in these two files and store them in matrices, which I call Tmat and Vmat for kinetic and potential. We can immediately look at these matrices to get an idea about their structure. And actually, you've seen these plots already in my lecture. So this is kind of the colorful plots I used to illustrate the three-body evolution of Srg. I evaluated this array plot command in Mathematica, and this is now the kinetic energy matrix. It looks remarkable at first sight. If you've never thought about the kinetic energy operator in a harmonic oscillator basis, you might be surprised by this nice block pattern. The blocks, as we discussed in the lecture, relate to the individual Emax or E, so total oscillator quantum number sets. So the basis states are arranged with increasing total or principal oscillator quantum number in three-body space. Therefore, there is this block structure, and the kinetic energy has a remarkable property in harmonic oscillator representation that it has diagonal matrix elements. That's this thin line here, and I'm not even sure that you can see that, and that it has off-diagonal blocks which couple to the neighboring principal oscillator quantum numbers. So therefore, this nice pattern. And this is now in three-body space, so that's already a super complicated basis. It's even more obvious if you look in simple two-body or even one-body matrix elements in a harmonic oscillator basis of the kinetic energy. You have the same type of structure with this blocks or the next diagonals for the kinetic energy. And the interaction part, that's this Vmat structure, that I've shown already in the lecture. So this is my initial potential, the structure of the interaction 2+3 body in the spaces. And again, you see there is a hint of this block structure, but the main thing is there are matrix elements everywhere. So black is 0 and brighter colors are larger absolute values. And you see even far off the diagonal, you have non-vanishing matrix elements. So this is the starting point, okay? So this you need as an input, and from there you can go. You have everything in this oscillator representation that you need to do either Srg or no-Koshal model calculations. Are there questions? Anything technical, unclear, or some physics question related to this? Okay.
Well, perhaps just from a technical point of view, you said something like the kinetic energy at this nice numbers like 50 and so on, because it was not the kinetic energy exactly. I didn't.
You will see that in a second. Yes.
Okay, thank you.
You will see that in a second. It has these nice numbers because I omitted the prefactor. You will see that in
oh, right. Thank you.
Okay. So now the Srg evolution. Okay. This is the first thing you can do with this. You don't have to. You can use this matrix as it is to do an NCSM calculation. But I think the fun part is to look at this Srg evolution in a little more detail. And essentially all the equations you need are again from the lecture. So we use the free space Srg that we discussed yesterday. And solving for an Srg evolution means solving this simple first order differential equation here for the Hamiltonian. And the right-hand side is given by this double commutator structure with a kinetic energy. So that's the intrinsic kinetic energy and twice the Hamiltonian itself. So that means if you multiply out these commutators, you have essentially products of three operators. So we are here still, so to say, at the operator level. Kinetic energy, Hamiltonian, Hamiltonian, and Hamiltonian kinetic energy, Hamiltonian, and Hamiltonian, Hamiltonian kinetic energy. So different orderings, all possible orderings. So these operator products do not commute. Therefore, these terms are different, and that's exactly what's encoded in these commutators. Now, we do have a matrix representation, a basis representation of all these objects, the Hamiltonian and the kinetic energy. So you can simply translate this operator differential equation into a matrix differential equation for the matrix elements of the kinetic and the Hamiltonian part. And you can just rewrite this thing, which is meant to be operators up here, in terms of matrices. And the only thing you have to be careful with, this is now really a matrix product that you use here. So this in Mathematica slang is this dot. So this is a threefold matrix product in different orderings, and that makes up the right-hand side of your flow equation. It is a coupled differential equation for, say, each and every matrix element separately. So therefore, you might think of, that's complicated with a standard ODE solver. It's not, it's essentially only a bookkeeping exercise, but I want to make it even simpler than the standard ODE solver. I will go to the most drastic approximation for solving such a first order differential equation, the so-called Euler algorithm. So probably you've heard about Runge-Kutta or other methods. You might also have heard about this Euler algorithm, which is absolutely brutal in terms of approximation. You get it if you just replace this derivative of the Hamiltonian matrix elements with respect to alpha by a finite difference. So you write that as a difference of this evolving Hamiltonian matrix elements for a flow parameter alpha plus a small delta alpha minus the Hamiltonian at flow parameter alpha divided by delta alpha. So that's a simple finite difference form of a first derivative. Okay. So there's a question. Did you say that the dot is for a matrix product? Correct. So these dots here are matrix products. So it's matrix times matrix, and the result again multiplied with a matrix. Exactly. So this is obviously in the limit of delta going to 0, kind of exact. It's a definition of your derivative, but we will use it with a finite delta as an approximation, a finite difference form, and it's the simplest one you can do. The great advantage of this is if you simply plug this expression into your flow equation up here, so replace the left-hand side by this difference, you can immediately isolate this Hamiltonian at the future point a plus a del. That's this here. And on the right-hand side of the equation, you have the original Hamiltonian, this H mod R, and the right-hand side of your flow equation multiplied with the step size delta, okay? So this is super explicit. You just can compute with all of the matrices that you have at flow parameter alpha, the Hamilton matrix one step into the future. So this is an explicit method for forward integration of a differential equation. It has lots of numerical problems, therefore nobody uses Euler usually, but it's good enough for a first attempt here. If you choose to do that yourself, then you're invited to use something better. Of course, you can do that with a Runge-Kutta algorithm from a library, for example. So there are many library algorithms which are capable to handle also coupled problems. So that's not an issue at all. And the matrices are not particularly large, so no problems there. But just to illustrate the point, I'll do it via this simplistic Euler. That means I have to set up a few things first. Number one is I start with an initial flow parameter, which is set to 0, okay. I set my step size, which is 0.0001, and I compose my full Hamiltonian, this H mod, which is kinetic energy plus potential. And these are the two matrices that are read in from the file, so that's my initial Hamiltonian. And then I kind of construct a structure which I use for storing results effectively. This is this VMAT Srg. So in this thing, I will simply keep Srg evolved potential parts of the Hamiltonian for later use. And this is just the initial VMAT, the initial potential matrix for flow parameter 0. And I'll later on store results for my future flow parameters bigger than 0 in this structure, because I want to use that then later for a no-Koshal model diagonalization. And now I do my Euler algorithm, and again, it's the most stupid way. I use this Euler step here for my small step size Adel, which is 0.0001. And I compute the correction or the change of the Hamiltonian and add it to the original Hamiltonian. I increase my flow parameter by the step size, and I do this thing 500 times. It's super stupid, nothing adaptive, no quality or numerics control in here, just brute force. And this 500 times with my step size that I chose gets me, after 500 steps, to a flow parameter of 0.05. Okay, I can do that, no problem. And here you see these mass factors coming in, so that's not super important, but therefore I needed the masses in my setup above. So once I'm done with these 500 steps, I take this new Hamilton matrix, subtract the kinetic energy matrix, the original one, and store everything that's left in my VMAT structure. So that's my Srg evolved potential part after 500 steps. And we can just do this. It doesn't take too long. Now running this block, and if it's done, it will tell me that it has completed this 500 steps and that we are now evolved up to a flow parameter 0.05. And the way I've written that, I can just run it again, and it continues another 500 steps. And I will do that in order to have two different flow parameters to compare with. So that, again, takes a moment. And if I'm done, I've evolved up to 0.01. And I have now 3 different Hamiltonians in total. The original one without any Srg evolution, one that's evolved to flow parameter 0.05, and one evolved to 0.1. And I can just have a look at these 3 different Hamiltonians, or better, the potential parts, after subtracting this kinetic energy piece again. This was a figure that we've already seen. That's the initial Hamiltonian. And then you have to pay close attention what happens, you might see or might not see, depending on the screen quality, that here these off-diagonal pieces became darker. So here you have still sizable matrix elements, these little bright spots, and they are essentially gone here. So that's what I showed also in my animation in the lecture. You suppress these off diagonals, and if you like, you can go on. You can just run that again, and you'll go further and further in the flow, and you can observe how this will change your matrix if you go on. Okay, so this is in principle it for the SRG part. And it's now just the diagnostics based on your matrices here and how the matrix elements evolve. But the interesting bit now is to really look at the performance of an NCSM calculation with this. So I will use these matrices now as input for the no-cause-shell model. And no-cause-shell model is now essentially nothing to be done except of solving the eigenvalue problem for these matrices. And these matrices are not large, so therefore I don't need to worry about fancy algorithms. You can use any off-the-shelf eigenvalue solver to do that. You do have, both in Python and in Mathematica, very powerful implementations of Langshas type algorithms available. So you could do much larger matrices, but it's not needed here. So therefore, NCSM is super boring. It's just take the kinetic energy and the potential matrix, add it, and for the resulting Hamilton matrix, solve the eigenvalue problem. And for Mathematica, this command is eigenvalues. And I don't even want to know all of the eigenvalues. I'm just interested in the lowest 5 eigenvalues, and I can tell Mathematica this by saying this -5. You can, of course, also get all of them. It's a few hundred, so that's not too much, but it's really not interesting. And from these 5, I also only pick out the very lowest one, since I'm discussing the ground state energy. If I do that, that's a super quick calculation. So it's done, it's done, it's done. And I've done that now 3 times for my 3 different flow parameters. This was 0, this was 0.05, and this was flow parameter 0.1. And here you see the ground state energies. It's -8.07, -8.08, -8.089, a little more still. So now here's a question for you. Are you surprised by that? It's almost the same number, but not exactly the same. Any explanation why this is almost the same number and why is it not exactly the same number? Any ideas?
Because it's a very light nucleus.
Yeah, I mean, so the number itself makes sense. So the binding energy of the triton, so that's the nucleus we are looking at, is -8.2 or so. That's okay. We are in the right ballpark. But now I told you all the time that SRG is good for accelerating convergence. And wouldn't I expect that I get a lower energy then if I go to the SRG evolved interactions? It's a little bit of a tricky question. You have to really keep in mind what we've done, because I've now just taken the complete matrix, all the information that I've used in this flow equation evolution, and I've stuck the complete thing into the NCSM calculation. So I've solved the eigenvalue problem for the complete matrix. If you now remember what the SRG really is technically, the SRG is a similarity transformation, or stronger, it's a unitary transformation. What happens if you take a matrix of 500 times 500 and you do a unitary transformation on that and compute the eigenvalues of the matrix before and after the transformation? What do you expect? Well, it's a unitary transformation. That means the eigenvalues of the matrix are the same, right? So somebody wrote that in the chat. The eigenvalues are invariant under unitary transformations. So you would expect, because I've done everything on the complete matrix, I didn't go to a smaller n max space where I could discuss convergence. You would expect that they are all the same, but they're not really the same. And somebody already mentioned in the chat, could have something to do with the Euler method. And that's correct. So the fact that they are not the same is because you have numerical errors, inaccuracies in this Euler treatment, because it's only true for, so this discretization with a finite difference is only true if you go infinitely small steps. We are going small steps, but they are simply still a bit too large. So numerical errors in this simplistic Euler evolution change the eigenvalues slightly. It's not too bad. That's okay. We can live with that. But this is something which you would get under control if you use a fancier ODE solver. This is something that's usually in a standard Runge-Kutta approach, captured by an adaptive step size control, so that you adjust your step size according to the properties of your matrix and do smaller steps if needed to reach a certain accuracy. So this is purely a numerical thing due to our simplistic Euler approach. Now, if everything is the same, because of unitarity, it's not quite clear how to see improvement in convergence. In order to see that, I have to really cut down smaller pieces of my matrix in order to, so to say, simulate NCSM calculations in smaller n max spaces. And I can do that. This is not super elegant. The matrix I started with is for n max 20. Now, the matrix I would like to consider now is steps in n max, something like 18, 16, 14, so going smaller by cutting out submatrices from my big matrix. The thing that's not really elegant here is you have to know how big the matrices for the different n max steps really are. And this is hard-coded here. So if you want to do that yourselves in some other environment, you might need these numbers. So this gives you just the matrix dimension for the n max 2, 4, 6, 8, and so on until n max 20 spaces. And if you want to cut out submatrices to simulate the other n maxes, the smaller n maxes, you kind of need to know these dimensions. You can also get that from the block structure of the matrix, which we discussed in the beginning, but it's easier to just take these numbers, which give you the basis dimensions for the smaller spaces. And I'm now doing exactly this. I cut out from my big matrix after the Srg evolution and also for the initial one, submatrices with these dimensions. And I do that with this take commando in Mathematica, and then again solve the eigenvalue problems for these submatrices. And I can quickly do that for the original guy and for the two Srg evolved matrices. And you have the raw numbers here. So I've output pairs n max and the corresponding eigenvalue, but we can look directly at a plot of this. So these are my three matrices. Blue is the initial Hamiltonian, the unevolved matrix. This orange is my 0.05 evolution, and green is 0.1 evolution. Down here is now this max, and this is the lowest energy eigenvalue. That means the ground state energy. All these curves meet at 20. That was this unitarity thing that we discussed a minute ago. If you go to the smaller n maxes, you see a drastic change in the behavior. So you stay essentially at the same value if you use the Srg evolved matrices. So then down to something like 10, and this was a magic nmax 10 that we also discussed in the lecture today, you're converged. So you can live with a much smaller matrix because you've suppressed these off diagonals. And only if you go still smaller, you start to see structure in the matrix which couples to your ground state. That gives rise to this energy change or this energy drop if you increase nmax. For the initial Hamiltonian, it kind of creeps down linearly. Okay, so there you've no indication of convergence in any of these smaller nmax spaces. So there you see how big the effect of this Srg evolution really is and how useful it is to keep your basis dimension small. Now there's one thing, if you're critical, you might ask yourself, okay, if I have to evolve in nmax 20 and then I cut down, this is kind of a game. I mean, if you can evolve at nmax 20, you can solve the eigenvalue problem at nmax 20, and you are done. And you've shown here that the initial eigenvalue problem at nmax 20 gives you the same value, so you can skip this Srg stuff altogether. This is correct as long as you stay in three-body world, where you can deal with such large matrices. Now imagine I want to do something like an oxygen 16 calculation with this. I would use the same matrix elements that I extracted from the Srg evolution in the three-body world in a large nmax in three-body space. And in practice, we use much larger nmaxes than 20. For typical calculations, for the production runs, as we call it, we use nmax 40 in three-body space to do the Srg evolution. Of course, you can never do nmax 40 in oxygen 16. So the real gain happens exactly at this interface where you do flow evolution, solution of the flow equation in small particle systems, two-body and three-body. And then you use these matrix elements in a 16 particle system. Via second quantization, you go up and you can use the same matrix elements there. And then you need to limit yourself to something like nmax 10 or 12. So when you need it really. So this is why this is a little bit artificial, and you might catch this point. But the real gain shows up if you go to the heavier systems with these Srg evolved matrices. Okay, there is a question. If we were to evolve the matrix up to a higher value of alpha, should we expect convergence at lower values of nmax? Well, we can try. The answer is yes and no. I will just run my flow evolution once more. So we can again go one step further to 0.15. And this is always dangerous because I didn't try that before. So something might go wrong now, but you're professionals, you know these things happen. I will solve the eigenvalue problem again. I just put the 15 here. And we add that to our plot to see whether things change if we go still further. And you see, yeah, a little. So now this red curve appeared in addition, and you see, yeah, in the very small spaces, I gain a little further. But this will stop at some point. So if you go 2, 3, 4 more steps, you will see that it doesn't improve anymore. And this is a reason of kind of the way we choose the generator, because we selected the generator with this, if you remember, this kinetic energy formulation. And in the basic discussion of Srg, the choice of the generator kind of gives you the basis with respect to which you diagonalize your Hamiltonian. So you would improve the diagonality with respect to momentum space matrix elements, but we don't do a momentum space calculation, we go to oscillator. And we see that the kinetic energy has this block structure, so there's off-diagonal stuff. If you go with something which is diagonal in momentum space, like the kinetic energy, to an oscillator basis. So you cannot really go all the way to a completely flat curve. But this is also not really needed, and that is also not really a favorable situation because of induced many-body terms. We discussed this no free lunch point, that if you go far with the Srg evolution, then you will induce more and more multi-particle interactions. Now, you might ask yourself, well, does that matter? It doesn't matter for the three-body system because we've done the evolution at the three-body level. So everything is there that I need to describe the three-body system. But if I go to oxygen 16 then there might be additional four-body terms, five-body terms, six-body terms that are induced by this Srg evolution, which I've ignored from the outset because I've done this evolution in three-body space. I will never see these induced many-body terms. And they will become much stronger if you go very far in the evolution. So typically, this is not the goal. Typically, we go with this evolution far enough so that we can converge the calculation in the model spaces that we can handle. This typical Nmax 10. And in this case, you would say, okay, I can practically converge this after my first Srg evolution to 0.05. I stick with this. I don't need to go further because my explicit many-body treatment in the NCSM can take care of the residual correlations. And I don't have to push or risk inducing more multi-body terms through the evolution. Yeah. Okay. Good. Are there more questions?
Oh, if I may ask, so just to be sure I'm understanding. So all calculations give the same result at Nmax 20 because the initial Srg evolution was made in Nmax 20.
Exactly.
Okay, so I mean, if I from the beginning, if I employed a smaller matrix for the matrix elements, let's say cut it to 10, then all the results will meet at Nmax 10.
Exactly. They
possibly at the wrong value here, there.
Absolutely. Yeah. Excellent point. Yes. So they would meet here.
Okay.
So that tells you with the space in which you do the Srg evolution, you also have to be kind of converged. The space has to be so large that you capture all the relevant physics that the interaction contains. And a good measure for that is you have to be able to converge the bare calculation for the three-body system in that space. And therefore, we don't work with 20 because you see this bare interaction curve still goes down. We go all the way to 40 in practical applications to do this Srg evolution to be sure to have all the physics. But if you do that in a too small space, then you've cut out all the matrix elements that live in this regime between 10 and 20, let's say. You've thrown them away from beginning and you have no chance to recover these correlations, this contribution to the energy, this information, because it's been projected away, thrown away from the very beginning. So this is an important point. You have to do this evolution in a big space, not to cut out any relevant piece of the Hamiltonian from the beginning. Okay, thank you. And so we can just check this on Triton, I mean a small system, and then we know that, for example, 40 is okay even for oxygen? Or no? You don't know that automatically. You should better check. The reason for that is here we just use one specific partial wave in the three-body world, one specific total angular momentum for the three particles. And that's enough to describe the triton in this case. If you go to oxygen 16, you will also have contributions from other three-body partial waves in there, and they might behave very differently also with respect to convergence. So this check should be done for the final calculation that you want to do. So that means you produce 2 or 3 different Srg evolutions with different truncations in three-body space and compare what the oxygen 16 calculation gives. And as soon as you see a dependence of your oxygen 16 result, ground state energy, on this size of the three-body space for the Srg evolution, you should choose a larger space. But this is important, and this is actually one of the most tricky things if you want to go to very heavy nuclei, because then it might not be enough to do this 40, and the 40 is just the thing that we can do. We cannot go much further, because then also these three-body problems become too large. So this is one of the very technical, deep down limiting factors in accurately treating very heavy nuclei. Not oxygen 16, but something like lead-208. There you will suffer from this limit.
Okay, thank you.
Mm-hmm. Okay, excellent questions. Okay. So, if there are no further questions, then, well, my idea or my kind of suggestion for you, if you want to dive a little bit into that, I mean, you can play the games that we just played yourself. I mean, you can either, if you have Mathematica available, just take this notebook and work with it. And for example, use a better implementation for the solution of the ODE, or look into the algorithms for diagonalizing matrices. Or you can take essentially the basic steps, which are really trivial that I did here, and re-implement them in a framework of your choice. So Python, C, Fortran, whatever is most kind of convenient for you, and play with it. And there are 3 things that you can kind of explore, which go beyond what I've done here. Number 1 is, as I mentioned, you can use a more sophisticated ODE solver to get around this numerical limitations of the trivial Euler algorithm that I use here. I mean, this is more kind of a technical thing, so there are no surprises there, but you would kind of learn how to handle such coupled first-order differential equations. Another thing you can do, which I didn't touch upon here, and which I find super exciting, but it's kind of an algorithmic thing and a computational question, which might not interest everybody. I'm super fascinated, as you might have guessed, by this Langshaw's algorithm. I didn't use it here and I didn't implement it here, but it's super easy to implement with the matrices that we have here. And for those interested, I would invite you just to try this super simplistic version of the Langshaw's algorithm that I also had in the lectures. You find this algorithm on Wikipedia, it's everywhere, no problem. Just Google for Langshaw's and try to implement that and try to work with it and see how it behaves as function of this Langshaw's iterations, how you approach to your true ground state. And then of course you can do all the games we did here with looking at different Nmaxes. You can also look at this critical case when you go to really, really, really large flow parameters and see whether things improve further. So just a question that we had. You can also go crazy and just reverse the direction of the flow, go backwards and see what happens. And if you're creative and you like the idea of this similarity RG, you could also try to invent new generators. So we use this kinetic energy commutator thing all the time, and everybody uses it. But there are many, many ideas and possibilities to choose a different generator. And the implementation is just as simple. And you could easily explore how these other generator choices, for example, a block structure, So something like the in medium Srg. You could really cut out a block from your Hamiltonian matrix, the one we use, and define that as diagonal, and you suppress the coupling blocks, the off-diagonal blocks, and see how that works. See how the flow changes the matrix, see how the Nmax dependence of your NCSM ground state energies looks like. So there are many things you can, in principle, try in this simplistic framework. Okay, so this is all I wanted to tell you. So you're free to do whatever you like. If you like to do something, I will watch the Slack all the time. So maybe not all the time, but if you have some ideas, some questions, some problems, some results, then it would be a great idea to just post it into this Ab Initio channel on the Slack stream. The others can see what you are asking, or if you have a nice plot or a plot where you don't understand what's happening, post it there, so then we can discuss it through the next days. So you're invited to do something, and I would be happy to see some activity there. Okay, so that's all. Other questions? Okay, so maybe you're all gone away, hacking away at your favorite code and playing around already. As I said, it's optional, but if something shows up and is communicated via this Slack chat, that would be great fun, because then also the others can see what you've done, what you've tried, and maybe you invent some new Srg or so. So we've tried many things, and there's still a hope that one can do better than this kinetic energy construction. Maybe you are clever enough to find something, and then we write a paper on that. Okay, so if there are no further questions, then I would just stop here. Thanks you for being back. It was a long day. And as I said, if you choose to do something and play around, just share some results, then we can discuss that. Okay, so enjoy your afternoon, and I think we see again on Friday, if I'm not mistaken. Okay, bye-bye.